We're going to move over to dye-sensitized solar cells now by Dr. Marina Freitag. And this is, as I said earlier in the opening, it's kind of the theme of this cost action that we try to get the various communities together so we can all learn from each other what is important to consider during lifetime aging, where are the differences, where are the similarities. So that's why we have so many different of those emerging technologies. And I think the communities have learned a lot from each other over the past years. And some of the mistakes of the early organic solar cell field have not been repeated, largely to this action which really brought together the various communities working on those emerging solar cells.
Hi, I would like to thank the organizers for letting me come here and tell you that yes, we are still alive. Dye cells are still here and we are thriving. And I will tell you the story how I got to be actually in this community a little bit. But first, because I feel like I should introduce what I'm actually doing, is I'm working on this part. So considering the whole solar cell, which consists of 2 electrodes, of course, and the dye-sensitized titanium dioxide, the dyes needs to be regenerated, right? Once they introduce an electron into the mesoporous layer. So, and this is also the most vulnerable part, right? Because it remains in liquid. So in terms of stability, this is a part where you should work first. So coming back to this, so once you absorb light in your dye, it will introduce the electron into the conduction band of the titanium dioxide from the excited state. And it will get back its electron for the redox mediator or whole transport material, which needs to get it back, of course, from the counter electrode. So. There have been many attempts, I guess, to actually introduce a new redox mediator to the dye-sensitized solar cells. Not as many as dyes, I would say, so there just still few exist. And to replace iodide triodide, of course. So this was one of the first ones introduced by Anders Hochfeld and co-workers in 2010. And it was also the first example that you can successfully use a coordination complex, for example, as a very effective redox mediator. So I remember the story always that another record thing. So the record was about 7%, I believe, in this paper, and it was also broken 2 weeks later, and further improved by Michael Gretzler, of course, introducing new dyes. So I came a bit later, actually, much later into the community, and I was supposed to work actually in cobalt complexes, but since this project was financed by Merck, they also decided we should no longer work on cobalt because somebody decided it's carcinogenic. So by accident, I got this. We were not the first one to introduce this copper complex. Actually, it was already previously done a couple of years before by Peng Wang. But we improved it a little bit. We introduced a new organic dye there, and we could show that the copper complex is actually really fast in regenerating the dye and very efficient on very low driving force. The problem there, of course, that we still were not as good as cobalt back then, actually. There is still something missing, and we introduced more redox mediators more recently, and just to play around a bit the redox potentials, actually. So you really have a small steps between just by moving a couple of carbons around the coordination sphere, let's say this way. The surprising part was here that not so surprising, actually, sorry. The diffusion is 1 magnitude better than in cobalt, so this is definitely an advantage. And of course, there's a small problem of absorption of the redox mediators, but of course, in comparison to our highly absorbing dyes, this shouldn't matter much. Another reason why those complexes are so efficient is that the organization energy for those complexes is extremely low. So no matter who tries to do copper complexes, please keep something in this position, because this position needs to be filled in order to minimize the transition between copper 1 and copper 2. So those were the first results. With our organic dye, so we got 8%, which was a good start, especially in comparison to cobalt back then, which in my hands gave me already 7% back then. So the regeneration kinetics were first measured with PIA, and it showed that all the complexes we introduced have a very good regeneration, and also on the time scale we are really much faster, actually, magnitude faster than cobalt. So it's about 1 microseconds half-life time. So then, of course, you go to EPFL, you bring the efficiencies a step further. So then we broke a little psychological barrier of 10%, also recently together with Yasmin. And the surprising part was here that, of course, as you remember, the redox potentials are a little bit different, which does not reflect actually in the open circuit voltages of the solar cells. So, of course, you can see this in the photocurrents a bit. So the question was for a while why this is the case, but our measures suggest that the recombination processes are just a little bit different. So, and more favorable for the tetramethyl bipyridine. Another interesting part is, of course, if you have such high VOCs, you can consider that VOC does not scale with light intensity, right? Photocurrent does. So this means if you decide to use the solar cells indoors, you can maintain high photovoltage, which is very important in order to drive devices. So why is it interesting? It's because the promise of photovoltaics is also that they will, of course, make buildings smarter and more efficient, but not just because for the energy consumption, but also to drive small devices inside. For example, IoT devices or any kind of sensors. So far, you have to wire those devices, or you have to introduce a battery. So with our solar cells, we could actually replace the batteries. And we could show this recently in a publication. What we did is we introduced a co-sensitized system with a new copper complex. And actually, I have to correct Anders a little bit. Sorry. We have actually 0.1 volt driving force, which is very low. So it's actually below the theoretical minimum. Works fantastically. And we did this, of course, to take a look on the one sun or full sun illumination. We got 11%. But the surprising part, of course, that our solar cells are in ambient light or low light conditions very good. So this is if you consider full or sun spectrum. So also in terms of kinetics, we could show that the co-sensitized system in peer or in time-correlated measurements is very well regenerated by the redox mediator. So we did this co-sensitization in order to match the light source we are using very well. So, and you have seen this yesterday maybe. This looks very nice, right? 29%, and I heard that they already got better. you have to be always careful with these efficiencies. Because of course, what we do is we consider what comes in and what comes out. And what comes in is already quite low. And that's also in terms of spectrum, very well matched with our absorbing system. So, but the beauty of dye cells is that you can adjust to any light source, right? You can just mix and match. What's interesting is actually those values, especially at 1000 lux, which is approximately what you have right now in the room. In order to replace a battery or in order to drive a wireless device, you need about 100 microwatts. So if I already have just a 2 square centimeter solar cell, this is plenty. Then this happened. This is our, a cover, journal cover for the first zombie paper, which we published also in 2015. And what happened, yes, we have a technician who wanted to have broken cells. So I thought, okay, those cells dried out. Here you go. He did complain a lot afterwards that they're actually still working. And we found out they are still working quite nicely. So this was the first time we did it already with the first complex. And we got, in comparison back then to the electrolyte, we really got better current. So the VOC remains and the photocurrent improves, which suggests that you probably suppress another recombination process there. Which we could also see in the electron lifetime since they're increasing for the whole transport material in this case. So, of course, like every whole transport material, the coverage or the pore filling within the solar cell is not perfect. So this means if you could improve this, we could also improve even further the solar cells, right? This is a little bit of the statistics. So you can see really a shift from the liquid solar cells to the solid solar cells once they dry out. And the surprising part was that if we compare just the intrinsic materials in terms of mobility and conductivity to spiro, which is doped, we are already there, and in some regard even better. Of course, what you do is you go to EPFL, you further improve your efficiencies. We also took the new copper complexes and did the same. Here you have the picture. If you really have this liquid electrolyte, you let it dry out, and then it works better. So in terms of stability, we could already show that they actually remain stable. Just the photocurrent goes a bit down. And for now, in terms of efficiencies, of course, we are still the best with 11%. So in comparison to all other whole transport materials, they're still below, and also in terms of stability. So I would like to thank the people who made this research possible. And actually, I'm building a small group right now in Uppsala, and I'm really looking for more people in my group. So please, if you know somebody, let them send me a CV. Thank you.
Thank you very much, Marina. I can immediately see 2 questions, and we have also time for some questions.
Thank you for the nice presentation. I'd like to ask you about the possible mass transport limitations in these complexes, because the cobalt complexes are known to have this kind of diffusional problems. I guess that with these complex processes, at least for the liquid electrolytes,
we could see those a little bit for the Finanzrolling complex, but it was completely reduced actually when we made the complex a bit smaller. So, I mean, if you consider also the diffusion, its magnitude better. So we don't have this problem any longer, actually.
Okay. I have to move over here.
Thank you very much for this nice talk.
Thank
I
you.
was wondering whether someone did some modeling for the copper complexes. You can predict ahead of time their oxidation potentials for the various copper complexes. So you have tried more than one copper complex. So the oxidation potentials can be calculated ahead of time. I mean,
Yes, and we have somebody who does this actually. It's let me see. So we have two people doing the calculations like this right now. This is Michele and Anna. Yes, you can. Thank you.
Okay. Thank you very much. No further questions. I don't see any further questions, so thank you very much.
Thank you.